Okay, welcome all to the ideas stage and the second day of Geo Week. We'll be having a number of presentations today, and we'll try our best to keep to time if we can. So, without further ado, from Minds Parties Tech, I'd like to introduce Pascal to come up and begin his talk.
Thank you, Jack, for the introduction. So we are going to discuss about co-design and how co-design could be a useful method to deal with application of Earth observation data. Where are we speaking from? My colleague and I, Raphaël Barbier and myself, we are not familiar with EO community, but we deal a lot on design theory and methods. So we have a chair sponsored by a lot of industrial partners, and we discuss on what does it mean to design and what are the engineering methods to increase the quality of designing. We organize in particular the Design Theory SIG, Special Interest Group, that is regularly meeting. Oh, sorry, not used with this tool, but it's coming. Yeah, exactly. We organize the Design Theory Special Interest Group, and there is a large community working on improving design theory methods, design theory derived methods. There is a strong renewal in design methods today to address new needs in innovation, needs related to new technologies. When it comes to Earth observation data, what is interesting is that now for a couple of years, we are going beyond the myths of data mining, just because in a way, the true issue is that everybody speaks of data as an ore, but immediately the question is an ore for doing what, and exactly how to refine the ore to do something. So finally, this analogy is really misleading, and the true point is really to design something based on data. And it's not enough to make data available to the largest possible audience, okay? So the point is really, what does it mean to co-design with data to finally get a relevant service for society? How we'll organize this ID stage. On a first part, I will insist on the EO-specific co-design issues. There are methods of co-design. I will shortly go through them, but they are not exactly adapted to Earth observation data specificities, and we have to underline this. Then, based on this, we explain what could be an EO-specific method, and I will give a brief illustration of this. In the eShape case, eShape being a very important project funded by European Commission in the H2020 framework, where we have 27 pilots providing Earth observation data and developing services with users. So specificities. Co-design in literature is quite important. Just to give you a brief overview, this is a notion that is born in so-called cyber-physical systems, and initially the problem was to integrate hardware and software in mobile systems. But step by step, it was seen finally as a quite easy method to have user involvement in the design process. And we can conclude from this short overview that we have co-design situation where there is a need for strong design with heterogeneous stakeholders and a strong relationship, and the relationship between stakeholders has to be reinvented or invented. And in particular, for this type of methods, we know now the co-design methods are more focused on specific situations where you co-design with end user. They really use the service lively. And second, we try to pool the design process by end user requirements, okay? Now, if we go to Earth observation data, how does it work? Well, the first thing that is very striking in Earth observation data is there is a quite a long distance between the value for end user and the Earth observation data. For instance, if you see that it's possible to use Earth observation to organize the logistic for tire change in Finland, it's not completely self-evident. You see the relationship between the data and the user. And even if from time to time you have a situation where Earth observation data for solar is used for solar energy, for instance, potential estimation, In a way, the problem is that you want to go beyond this and find new applications. So the problem is always that finally the relationship between data and value for end user is really, really not self-evident. And if we compare this situation to what I said before, it's clear that we are in a situation where there is a need for design, there are heterogeneous stakeholders, there is a relationship between stakeholders that has to be created, but when it comes to the design methods, this is not with end user, this is with data users, which is not the same thing. And so they are from time to time quite far from the final users themselves. And second, it's not pooled, but it's more a form of data push, which is extraordinarily complicated to organize. Where it's not pooled by user, but it's pushed by data provider. It needs that finally you have to get methods that are inspiring and stimulating needs. So this is why the classical methods are not completely relevant in that particular case. Now, if we go deeper in this, look at the users we have. Finally, the question is, do we have the relevant user? What is useful for him? And is it a usable information for him? And we have a first class of problem where finally the user is identified. Okay? He has a problem, and it's clear that the data is a new resource to solve the problem. This is a good news. And second good news, the user is able to use the information. So this is a kind of ideal case. And in that case, it's true that you can organize co-design as a way to optimize user friendliness in a way. But even here, immediately appears the fact that it has to be engineered, and you have to imagine a system that is good with quality, after-sales service, etc., etc. So this is probably not necessary to go only, it's not enough to go with the user, but you have probably to organize a co-design process with engineering experts, which is quite unexpected but very important. Another direction to discuss this ideal situation is to say, well, in situation, the user is identified, the usefulness is clear, but the usability is not here. You have to provide toolkits, techniques to help the user make use of the data. So usability has to be designed, and it's a quite difficult issue. Even worse, there are situations where you know the user, but finally it's not clear how the data resource is important for him. So your usefulness of data is not here. And even worse, you have situations where finally you're not sure that you are working with a relevant user, and you have to prospect for unknown user for the moment, future users. So you discover that step by step, the co-design process is designing usability, designing usefulness, or even in a way, designing the system of users. So it's extraordinarily demanding. You see, the kind of method that we require for this, we need method for that, and we need method for this. Okay, this is where co-design needs are. How to build on this? Here we have method. It's quite easy. But here we need new methods, and here we need new methods that will increase the robustness of the service, and here we need methods to design more innovative services. So this is where there is a need for co-design methods. Well, I think I'm short, so I will skip. I had an example to a very easy example. If you want to know more about it, I can keep it for questions. I skipped. And now, what can we propose as new methods? The good news is that the design theory community and all the work that have been done can help deal with this kind of problem. The first thing is there is a negative result. If you have no situation in the upper left corner, there is a very, very few chances that this situation will emerge alone. Naturally. Generally speaking, this situation is quite rare and difficult to emerge by nature. We can explain this. It means that there are a lot of fixation, and in a way, if you don't organize generativity, there is a good chance that you never will go here. So in a way, it's necessary to find methods for the other cases. The positive result is that today, the progresses in design methods help us to organize this kind of process. Designing usability, designing usefulness, designing new users is possible. So it's good to know this. And the second positive result is that we can also characterize what is the final result to be get. So it's a bit abstract here, but we can explain what has to be designed exactly and quite rigorously. So it's possible to not only propose a method, but also to control the method, which is quite important if you have a kind of quality assessment. And third, well, it's also possible, based on existing knowledge, it's also possible to explain how to do this. And the first point, if we want to develop co-design method, is try to explain what is the ecosystem of actors. The first point. And now it's possible to explain how we are going to develop EU-specific co-design methods. And the first issue is, it's not enough to have co-design actions, but the first point is you have to be clear on the diagnosis. What exactly are the methods you require? So the first point is not to push and immediately implement a method, but the first point is to organize a diagnosis to be sure on what are the good methods to be set in place. So I will insist a lot on this first diagnosis process, which is a less self-evident. First, after diagnosis, finally the co-design action in itself is then becoming quite easy. So the really strong issue is the diagnosis phase. How can we organize a diagnosis phase? This I will explain directly on the E-Shape case. So E-Shape, 54 partners, 27 pilots in 7 showcases on many different applications area. And what we have done on E-Shape, the first thing was to try to represent who are the actors. If we think about a kind of data-driven ecosystem, how is it organized? And the first effort we have done with our colleagues is to try to represent for each pilot the kind of data ecosystem, separating the data sources and the user community and trying to understand how the data sources are related to user community. And in each case, what is interesting is that we see that the pilot is in the middle, is using data, is transforming data in a more abstract and non-contextualized information. And then this information is provided to the data user and provided in a kind of actionable way. This has to be provided in a form that is actionable by the user. And the critical point is what happened here, the relationship between the pilot and the data user. And we see in this scheme that this is, in each pilot, this relationship, this chain is already organized, and the true issue is to enrich it, finding new user, or occasionally trying to find new data to have more relevant services. So this explains how the ecosystem is organized. Based on this explanation, so we did this for each 27 pilots. It's not finished. We are going to do this. This is an ongoing process. But for instance, this is one of the pilots in this framework, it's hard for me. This is one of the pilots. Here, this is our colleague from Armin. And this is an energy pilot. There is a quite complex scheme. And then, based on this scheme, it's possible to identify where are the key critical relationships. So what you see here is a situation where we can identify that there is a co-design need. And for each of these co-design needs, it's then possible to have the co-design action. So here we see the technique we have to identify the co-design needs. We have done this. We are going to do this on several pilots. And there is an interesting result. So this is a process we follow to do this for each pilot. We discuss that with them, and we have a kind of pre-diagnosis and then a conference with them, Colte, Telco, etc. What is interesting is that in the end, we have already an interesting result. The relationship between the pilot and the engaged user, thank you, 2 minutes, yeah. The relationship can be reinforced and strengthened. This is a classical representation. The relationship between the pilot and the users is unsure. It's unsure, but the users are already interested, and you want to understand where are their problems, what is usefulness for them, and what is usability for them. And in that case, you are quickly in the upper left corner. This is quite good to deal with. But we see immediately that we have also a lot of situations where the relationship here is weak. But the problem is that maybe the user you are discussing with is not exactly the good one. And here you need a co-design for dealing with unknown user. This is another type of co-design action that has to be set in place, and that occurs quite often in the pilots. Another situation is that, paradoxically, the relationship with the user is good for the moment. It's not weak, it's strong. We have good users, they are ready to use the data, etc. The situation is quite positive, so there is no co-design need, apparently. It works already. But in that situation, the problem is that it works, but it has to work at a kind of industrial level. So the kind of co-design you did here, it's not with the engaged user, it's much more with the stakeholders that are providing data and the engineering teams that are helping to support the design process. And last situation, it's possible that you have a well-organized relationship with some users, but for the future, you have to discover the future users. So you have to extend your user base. And here you need a fourth form of co-design action. So you see how the framework helped to identify 4 types of co-design actions that are quite different. And to conclude, we can, first of all, understand that there is some specificities to be addressed based on the variety of data user and the type of thing that has to be designed. Usefulness and usability have to be designed. This leads to a strong diagnosis phase that was quite unexpected, but it's now ongoing and it's really fruitful. And it's interesting that we see co-design activities that are not directly made by non-users, which is quite a discovery and interesting for the future research. More generally, it shows that eco-specific co-design requires specific competences to do all this work, and it might be interesting to discuss in the GEO, in the group of Earth observation, how to strengthen the capacity to deal with co-design engineering, we could say, co-design methodologies. And second point, if we go beyond co-design methods, here we discuss only on method, but the true issue is what does it mean to organize a society of users inside the group of Earth observation? If the relationship is so complex with users, maybe it has to be institutionalized inside the group of observation. This is more for questions. Okay, thank you.
Thank you to Pascal and also to Raphael for preparing that presentation, in particular reminding us that usability and accessibility is only the first step, and rather we can take that next step into inspiring our future users, both known and unknown. Our next speaker is Philip Heinrichs from the OECD Sahel and West Africa Club.
What is the button? Yep. Okay. Perfect. Hello, everyone. Good morning. I am Inho Heo from OECD. Today, I'm going to present you the database, Africa Police database, and the various usage of the database. So, to explain you what is Africa Police, I prepared some short video to help you to understand. So, sorry. So, as you can see, Africa Police start from the satellite image, and thanks to these days very high resolution satellite image, we can track down every single building. And what first Africa Police do is catch the outline of the agglomeration of these buildings, and then by superimposing with the census data, we estimate the population and catch the built-up area. So this is a city called Ado-Ekiti in Nigeria, and it has a number of population, 380,000, and built-up area of 92.98 kilometers square. And Africa Police has two definitions of city, and one of them is an agglomeration is considered urban if it has a minimum of 10,000 agglomerated inhabitants. So here's a city next to Ado-Ekiti called Ikere in Nigeria, and number of population is 170,000 with a 21 kilometer square built-up area. And in Africa Police, these two cities are considered in separate city, and the reason is because the building from Ado-Ekiti to the building, the closest building in the Ikere is 1.93 kilometer, which is further than the distance 200 meters. So that's the second definition of city in Africapolis. An agglomeration is a continuously built up and developed area with less than 200 meters between buildings. So when the city grows and the building become closer to 200 meters, we say that the two cities are being merged, and we keep the name of the bigger agglomeration at the time of being merged. So we catch like this built-up area in whole continent. So these are the two definitions I just told you, the Africapolis. And why is it so important and interesting is because each country has a different definition of cities. So each country has a different definition of city, and the different definition can be categorized by three definitions. One is administrative definition, and second is numerical definition, and third is the mixture, both administrative and numerical definition. So as you can see, Egypt is the example of administrative definition. So it is defined as governorates of Cairo, Alexandria, Port Said, Ismailia, Suez, and the district capitals. And then numerical definition is simple and clear in Ethiopia, localities with 2,000 inhabitants or more. And the Cameroon is the case, the mixture of between administrative and numerical. It is administrative centers of territorial units or any localities with 5,000 inhabitants or more and with sufficient socio-economic and administrative infrastructures. So this Africapolis definition, it is make a big difference. This is a satellite image of Egypt, and as I showed you from the video, we again catch all the built-up area and estimate the population in these urban areas. And when you follow this administrative definition from the country, the national definition of cities, the level of urbanization is share of urban population from the total population. So when it is 40-30%, that means the 43% of the population live in urban area. So with the national definition of cities, it is 43% in Egypt. But when we use the Africapolis, the two definitions, then it is up to 93% in 2015. So with these two definitions that we detect all the agglomeration in the continent. So for bigger than 3 million inhabitants, we have 25 number of agglomeration with 146 million urban population and then 31,000 built-up area kilometer squares. And for 1 to 3 million, 49 agglomeration, 300,000 and 1 million, 148 agglomerations. You can see when the threshold is getting smaller, it is well known that there are few big cities, but very many small cities. So for 100,000 to 300,000, almost 500 number of agglomeration. For 30,000 to 100,000, 2,000 number of agglomeration. And for 10,000 to 30,000, there are almost like 5,000 agglomerations. So in total, with this Africapolis definition, we found 7,617 number of agglomeration with a 567 total urban population. And it contains the 139,000 kilometers square. And when I put those number of agglomerations in the 64-kilometer grid, and we could find like some very clustered area. For example, in the Egypt, I showed you that it was 93% of level of urbanization. You can see how densely they live in the country. Those very dark area, each 64-kilometer grid, more than 10 agglomerations are there, and it is along the Nile River. And below that, there's Ethiopia and crossing Sudan with a high altitude area. And here is surrounding the Victoria Lake, the clustered area, and here Johannesburg, Lesotho, Kingdom, Eswatini area, and here from the coastal to the inland of Nigeria, there's a big number of agglomerations, and here the coastal area of the North Africa, again, like a very clustered agglomeration exists there. So this is one of my favorite map of Africa, and this is I think many people saw it. It's a night light in Africa. So by using this night light satellite image, we made some very interesting analysis. So we took the year 2012 of night light satellite image and 2019 night light satellite image, and by comparing it, we calculated like how many cities already had a light in 2012 and how many cities had a new light between 2012 to 2019, and how many cities never had a light neither year 2012 and 2019. So in the continent-wise, you can see among 7,600 agglomerations, 5,000 cities had both year 2012 and 2019 the night light, and then 767 cities have the new lights between those periods, and 1,700 agglomeration had no night light both 2020 and 2019. And the circle next to it is actually in population terms. You can see the number of the no lights is 1,700, but this is in population term. You can see that actually no light cities are like mainly in the very smallest threshold. So most of them are like a population between 10,000 to 30,000. So even though there are very many number of agglomerations, but in the population terms, it is only 6% of it. And I will show you each region. So North Africa has like has the lights everywhere in 2012, and there's only one city in the region that has a new light between 2012 to 2019. So the zoomed area is Tarabulus in Libya, also called Tripoli, the capital of Libya. So there's one city next to it has a new light between the time. All the other countries has like both 2012, 2019 has a light. And here, West Africa, you can see that among 2,400 agglomerations, 400 agglomerations have new lights. And you can see Sierra Leone, Liberia, Chad, for example, have like, there are many agglomerations with low lights. And it is very interesting that actually it is linked somehow that those three countries are actually have the lowest GDP per capita in the region, and it shows some correlation with the night light. And the zoomed area is the Kano in Nigeria, and it is as known as a city feeding the region, since the biggest food market locates in Kano. And it is very hopeful situation that the surrounding the small agglomerations having new lights in Nigeria. And you can see there are many over the region. There are like new lights between 2012 to 2019. And here is the West Africa. Actually, this is mislocated. It's here, Khartoum, the capital of Sudan. East Africa also like there are like 300 cities have a new lights. And you can see South Sudan has very many cities with a no light neither year. And here is Central Africa. Central Africa, very interestingly, like very many agglomerations have no lights, and it is mainly because of Democratic Republic of the Congo. You can see those gray points These are the agglomeration, have no lights both the year 2012 and 2019. You can see again, like from what I show you from the cluster map, the Victoria Lake locates here, and there are many new lights going on and development is going on surrounding the area. And here is Southern Africa. It is always very interesting to see the dramatic result when you do the analysis. You could see that North Africa and Southern Africa, there are like very few no lights city and very few new lights either. So it is in a different speed of the development stage. And zone area is Johannesburg in South Africa. You can see like in South Africa, actually every 500 agglomeration has lights in both years. So in the end, like with all these 5 zones, we have this beautiful map. So this is one example of the Africa Police, and I brought actually the beautiful postcard of the Africa Police database. If you're interested, you can take it over. Thank you very much for the listening.
Thank you very much, Iho, for sharing some of those very stunning images with us. Our next speaker is Beryl Morris from Turn Australia, and she'll be speaking about the creation of Australia's National Environmental Prediction System.
Good morning, everyone. I'm going to tell you about an idea that is developing in Australia to develop a national environmental prediction system. As you can see from the heading, I'm giving away the answer already in the beginning. We're trying to federate a whole lot of things that already exist in Australia to make a national environmental prediction system. So the question is, how is it possible to even think about having a national environmental prediction system? This is quite a difficult thing to do. It's because in Australia we have regularly developed, under the Australian government, a national infrastructure roadmap where a period of time takes place where people go out and consult with the community as to what is needed in order to support Australian research and decision making and economy and so on in Australia that can be provided through infrastructure. And we had one of those road mapping investigative exercises in 2016, and that led to what's regularly called the National Roadmap. And shortly after that, the government's response to the consultations of the roadmap led to another document being brought out, which identified investment for the next period of time that would go into national research infrastructure. And in that document, it was identified that there would be a scoping study carried out on a national environmental prediction system. And that's how come I get to be here, because Australia already has a lot of national research infrastructure, and the group that I'm heading up is called the Terrestrial Ecosystem Research Network, and we're the land observatory of the country, taking long-term measurements of changes in the environment. And Turn was given the task of managing the scoping study that would be carried out on developing the possibility of developing a national environmental prediction system. The funding that comes, goes into national research infrastructure, such as Turn, comes from a government initiative called Heinrichs, and this is a really good thing that Australia has, that all of our research infrastructure is funded under one scheme, and it is very specifically for research infrastructure. It's not a hybrid scheme. There are other funding schemes that fund the research component, and the purpose of national research infrastructure is to make the investment in research by the Australian government much more efficient, but by providing those very large-scale infrastructures. So why would we want to have a national environmental prediction system? Well, it's because we want to get to be able to have an integrated understanding of the environmental, economic and societal needs for our future states of environment. And you notice those three items, the environment, the economics and society. And it's considered that unless you put those three together in doing the consultation for a national environmental prediction system, then it's not going to, we're not going to get the societal permission to put in place a prediction system. You can imagine how difficult it might be if people don't trust an environmental prediction system and it is forecasting all sorts of changes in the country, such as that comes from increased sea level, where houses might depreciate in value. There might be greater risk of diseases from where people live. So we have to have society brought along in the system. So how are we going to go about this? When there were a few parameters set for the scoping study, and it was felt that the investment that has already been made by the Australian government in national research infrastructures should be leveraged. And so the idea is that there are already a very large number of entities in Australia that are providing some of the answers that are needed to make a cohesive environmental prediction system. And so we have all of the research infrastructures that are funded through the Australian government's NCRIS scheme. We have government departments and instrumentalities such as Geosciences Australia, the Bureau of Meteorology, CSIRO, just to name a few, that all have components of what is needed in a national environmental prediction system. So the scoping study that's being undertaken at the moment is developing a system architecture for the National Environmental Prediction System that takes into account all of those pre-existing activities. And so the rationale that we have for the National Environmental Prediction System is that it be a networked infrastructure that allows the integration of the environmental observations with predictive modelling that might occur in individual institutions already, to provide the evidence-based advice that's needed to assist the economy and the well-being of society in Australia. Now, the reason that this is the good time to do an environmental prediction system scoping study is that there's been a great deal of maturity over the years in Australia by having funding for national research infrastructure, having very dedicated systems for funding research and modelling and so on. So that growing maturity has been a good base to build upon, and there's an accelerating need by the decision makers of the country to have a basis for decisions that it comes from an evidence base, something that they can rely upon. So the principles that have been identified for how we will build this system is that we're going to adopt things or adapt things that already exist, and a little bit of invention to glue things together. So we will network all the existing infrastructure where possible. We'll enhance and accelerate things that are existing that aren't quite fit for purpose at the moment. They might have been set up for another reason and they don't quite have all of the ingredients that are there. We're going to grow the development by prioritising the end users that might have most need for an environmental prediction system. And so we're out consulting at the moment with groups in Australia that think that their business would be improved or their research would be improved or their government decisions would be improved if they had a reliable prediction system. And so things like regulators, people in the health industry, There are a whole range of things that rely upon knowing changes to the environment that are well outside of the area of environment that need that sort of thing. Where we're going to be as collaborative as possible so that we use all of the information systems that are already in existence. So Australia has a climate computing system called Access that will be used and adopted into the environmental prediction system. And we will try to be as interoperable with economic and social systems as possible. And I think this is the really important diagram to bring those sorts of ideas together. It's technically possible to develop an environmental prediction system. We can gather the information, we can put the technical components together. We're very clever in that area, but do we have the societal, the social agreements and so on in place to be able to adopt it? What do we need? How do we protect people against forecasts and predictions that aren't quite right? How do we put in place the systems to protect sensitive information? So we have to have a very integrated social technical design for a national environmental prediction system. This can't be stressed enough. So we have taken that on board, and we are trying to identify all of the who components, the social architecture that is going to be involved in a national environmental prediction system. We want to find out everyone that's out there that will be affected by, they'll be the users of an environmental prediction system, or they'll be the suppliers of information into the prediction system, and then we want to know what we're going to put into it to support the access and the management and integration. And so that's our information architecture that we're going to be working on. And then there's the technical architecture that works out how it all goes, how we support the information flows and the data management. The consultations to date have been quite... sorry. I have been pressing the wrong button, sorry. So you have been missing all of this. That was my wonderful diagram that you should have been seeing. And these are the who, what, and how elements. And now we're into the part that we've got to, with our consultation to date, we've identified a very large number of groups that already exist in Australia that have got components of our system. And we've identified some of their strengths, and we've identified areas that there is going to be a need for investment. We really do need to know what are the measures that we're going to have as consistently available to people. So the idea is that we finish up with a system of systems, that we have interoperable models across the group, and that we're supported by a data hypercube. If we don't have an environmental prediction system, a NEPS, then the cost of that is that we're going to have a very fragmented, ad hoc environment. We're going to have opportunity cost, and it's going to be quite costly for people as they try to do things alone instead of leveraging each other's activities. Our ability to do national planning for environmental change will be severely depleted. And the decisions that are around infrastructure investment, energy, human health, they'll be made, but they'll be difficult for the scientific community to contribute and coordinate their activities with those. So we think that the investment in environmental prediction is going to be in the interests of the country. And we've identified some challenges that are there. So obviously if we get some of there's a great push around the world that environmental prediction should start with near-term forecasting. And if we get some of those wrong, then people are going to become very sceptical about the idea of a national environmental prediction system. And so we do have to focus on the long-term perspective and making sure we're using long-term data and that we're doing a lot of backcasting through it to prove that the predictions are worth it. And we have to bring people along on the system because people aren't very good at thinking about probabilities. They will probably have to adopt a new language when we're talking about forecasts for them, so that we talk about threats and scenarios and consequences. And we need those people from society in the room with us, helping us evolve and develop the environmental prediction system, because that means that last quote, when you incorporate the users into the decision, they can't blame you when surprises happen. There'll always be surprises, but it's better to have us working on it. So what can you do? Well, I'm hoping that you'll actually go to our National Environmental Prediction System webpage, and I've done it again, and the link is on this page, or to email us, or to find me in the room during this event and have a little chat to me. But we would really like to get your perspectives on how we should be developing a national environmental prediction system. Even if you're not from Australia, it doesn't matter, because we're one planet and our environmental prediction system will be something that will need to link in with every other country, and so we want to get the interoperability right from the beginning. Thank you.
Thank you for that speech, Beryl. Next up, we have Patrick talking about internal migration trends using mobile data in Rwanda. Is Patrick here? No? Okay, I'll just be one moment. Okay, so we will just move on to our next speaker, given that Patrick is not here. So I'd like to invite Martin Schlodock up from the Federal Institute of Geosciences and Natural Resources for Germany. Thank you. Just be a bit mindful when you tap the laptop. Okay.
Good morning, everyone. So, can I get my presentation? Okay, so today I want to talk about how we at the BGR are working with hyperspectral data in the sector of the exploration of mineral resources and arable land use. I would like to start with the background, the motivation of our work. It's a major challenge for a modern society to use natural resources efficiently and sustainable. That means that the mining industry have to address the increasing needs of the high-tech industries, for example, to provide critical raw materials such as rare earth elements or lithium, for example, for the e-mobility. And the same as for the sector of arable land use. So it's challenged by the sustainable soil management. And so to address these challenges, new methods and technologies has to be developed, for example, as a more efficient exploration of raw materials or to enhance spatial characteristics or characterization of soils. So we think that hyperspectral imaging is such a technology in the field of remote sensing which really can support and provide such information to address these challenges. I would like to introduce first what hyperspectral data is, for those who are not so familiar with hyperspectral data, and I like to start with the multispectral data. So a multispectral data set we all know from Google Earth or from Landsat systems, so that actually the Earth is scanned in a, oops, wrong way, for a certain wavelength range, here from 0.5 to 2.5 microns. The surface is scanned with a couple of broad spectral channels, which are shown here as this gray bar, and we get for a certain wavelength range here 2 to 2.5 microns, just a single value. So we can't do any mineral identification there, just we can look for mineral groups. If I look to a hyperspectral data set, so we get much more information about the material on the surface. So we can see here mineral spectra, which are from laboratory measurement, and we see in the mineral diagnostic spectral features, which are resolved with the hyperspectral data and which you can't see in the multispectral data. So, and the hyperspectral sensor records those certain spectral features, which we call absorption features, in single narrow spectral bands, and this allows us to do a mineral identification. So that's a benefit of hyperspectral data. Why can we do the mineral identification? Just briefly, we have electron transfer processes to detect elements like iron, nickel, copper, or rare earth elements, which are mostly between 0.5 to 1.0 microns in the wavelength range. We have vibrational processes as overtones, combination tones, which we see in this wavelength range from 1.0 to 2.5 microns, which is depending on the mineral compositions or chemical compositions of the minerals. And we have fundamental vibrations, which are far beyond the 2.5 microns wavelength range. It's between 6 to 14 microns, where we have the fundamental vibrations from dehydrated silicas. And how can we describe those informations? This is done by so-called feature extraction or spectral feature extractions. It means we are able to describe such a mineral feature, here for example the kaolinite. So we describe the shape and the position of the mineral feature, and that's for the identification. And we describe the intensity, which is done calculating the depth of the spectral feature. It's for quantification. And a second option to analyze spectral data is to do an end-member-based classification, meaning we develop spectral libraries, which includes known spectra of well-described minerals, for example, and in the analysis we compare this known spectrum with an unknown spectrum, and the degree or the order of agreement is a measure of if we targeted a mineral or not. So how do we apply these? We use imaging spectrometer as a BGR. We have a drill core scanner, which is shown here on the right-hand side. There are mounted 3 cameras so that we can cover the whole wavelength range of remote sensing. We can run pixel resolutions between 25 microns to 1.5 microns, so we go from the microscopic scale to a mesoscale. We use terrestrial and airborne systems, which is shown here as the UAV. It's shown here as tripod-mounted systems to scan outcrops, or we mount the system on a BGR-owned helicopter. So we can do here the applications up to 1 centimeter and larger pixel sizes, depending on the distance to the target. And finally, we use point spectrometers, as shown here in the field, for validation purposes. And now I come to a few results. One major work was done on drill core analysis, here a rare earth deposit in Germany called Storkwitz. We met the rare earth elements in the bulk mineral distribution, and we were able to identify 3 mineral phases which bearing the rare earth elements. The spectral feature of the rare earth elements are these 3 absorption features, and these two are the most dominant one at 800 nanometers and 650 nanometers, 750 nanometers. We identified by comparison with reference spectra, and here are the locations of the spectra, or the pixel for the spectra. And if we now map just the feature of the neodymium, we can see the abundance distribution in this part of the drill core. So we see there's enrichment in red, and the blue areas are low of rare earth elements. And we detect the neodymium, which is the strongest signal, but we can use the neodymium as an indicator for the other rare earth elements as well. We can map the distribution of the mineral phases, it's shown here. And finally, to make the complete picture, we can analyze the whole drill core with the mineralogy and use the thermal infrared wavelength range to pick also the quartz minerals so that we have a complete picture of the drill core. We can transfer this information further to work in outcrop mapping. Again, this is a rare earth bearing deposit in Sweden, in Nordkär, which is a heavy rare earth element bearing system. The proxy mineral is the udilite, and again, we have here these little wiggles, which are the neodymium information. We can map everything. We see there's a distribution of the neodymium in the upper part of the outcrop, and the lower part doesn't show it. So we can also use such an information for further exploitation approaches. Another project using hyperspectral data is in this project HypeGeo. Actually, this is a project where we want to use geophysics data together with hyperspectral data, meaning the purpose is to combine surface information with undersurface or with deep surface information. And so this was set up using hyperspectral data from lab hyperspectral in the field. We used multispectral data from satellite system and the gamma ray spectrometry and gradient magnetics. So what we can see is with the satellite system, we can distinguish between AL-rich and AL-poor mineralization, but we can't identify the mineralization. So then we use the hyperspectral terrestrial system. We scan this mining phase in the back, which is shown here. So we can identify the mineralization. We can see areas with an enrichment of muscovite and other areas enrichment with chloride. That means in between this sharp border or sharp edge, there's the former ore body in that area. So we can also map alteration patterns. In agreement with that is the potassium spectrometry, where we see here again a bit of increasement of potassium here as well, which is related to the ore system. And finally, the magnet gradient shows this as well in that area. So that's a really good, nice example how we can combine hyperspectral data with geophysics data and to make the exploration more reliable. This is done in 2015. It's an hyperspectral airborne campaign, which was thought as a pilot for the preparation of the NMAP mission. NMAP mission is the German hyperspectral satellite mission, which will be launched in 2020. The idea was to develop a hyperspectral expert system for exploration, meaning that we want to spectrally characterize deposits and their geological setup and the detection of possible mineralization zones. Here's an example of that area in Achanes. It's in northern Cape of South Africa. It's a ZX massive sulfide deposit, basically lead and zinc, a bit of copper as well. And if we focus on that area, we can see that's here in a zoomed-in product. This is the mosaic. It's derived from 45 flight lines. If we look closer to a certain area, which is shown here, this is a mineralization zone, which actually hosts the mineralization, and we see a bit of color differentiation, and this nice orange-red color shows the Rams formation, which includes the mineralization. And if we classify it, we get a nice picture. We have all the surrounding mineralogy, and we can see in yellow the iron anomaly, which was told us from the exploration geologists that if you want to look after, or if you look for a mineralization, look for the iron content. And finally, within this iron anomalization, we were able to identify hematite, here shown as red dots. And if we went into the field, here are the hematite exposure outcrops, and this is the gossan. This is the surface expression of the mineralization. And so if we map this over the whole Ramsberg, which is shown here on the left-hand side. So we can see it's mostly at that area where the Ramsberg formation crops out. And this was done 2015. And if we look at satellite data from 2018, so 3 years later almost, we see that exactly in that area they are doing the mining activities. So that's a really good verification that we were able to localize the mineralization and to add to the exploration. So this is apart from mining. For soil, we recently started 2 projects. One is to derive soil parameters from Sentinel-2 data in combination with hyperspectral fieldwork. The idea is to derive the soil parameters, clay content, mineral compositions, organic carbon, soil moisture, fraction of soil skeleton, and surface roughness. It's done in the federal state Baden-Württemberg in the southwest of Germany. And since we are just starting this project, we have done field measurements using an ASD point spectrometer. We have done laboratory measurements, see which information can be derived from the spectral information, and now the next step is to transform this to Sentinel-2 data and to see what can we derive from this information. And the second project in soil management is the regional characterization of soil properties, and using as well a combination of remote sensing data, geophysics, and soil science or geopedology. And this is a project where we want to go in a regional scale, not only looking at certain outcrops. So we are doing some tests in Germany. If they are successful, it should be transferred further to larger areas, for example, in Morocco. And what's the story behind this is that we use soil information, we use mineralogic information in different scales, this row. We use geophysics and try to combine and to find areas which are most homogeneous, and just to really characterize the soils to make the soil management capabilities better or enhance them. This shows us that this project is also in different scales. So we're working with satellite data, with airborne data, with UAV data, and finally with field data, so that we merge all the different information in the different scales and to see what ends up at the satellite. So finally, you can say for exploration and mining, hyperspectral data is quite fruitful. We can identify an indicator minerals for mineralization. We are able to spatially mapping mineral phases and alteration patterns. We can do vectorizing, meaning we can pinpoint to a certain mineralization. And we have done the preparation work for upcoming hyperspectral satellite system as NMAP or SHIME in the future. And for the soil as a resource, we are starting to characterize the soil properties, and the most important thing to do it in a regional scale to work in large areas. That's it. Thank you for your attention, and I'm happy to answer questions.
Thank you, Martin. Next, I'd like to introduce Thomas Legge from the Federal Institute of Geosciences and Natural Resources of Germany.
Thank you. Yes, it's a long name for institution, and we just say BGR. This is kind of Geoscience Australia for Germany. So, and I will talk about the opportunities of, let me say, satellite-borne radar interferometric ground motion service in Germany. Okay, this is the one. And there's another word I will use for radar interferometric things. This is INSAR, just to don't puzzle you with the using of words. So we will talk about the ground motion in Germany that happens, and the motivation and concept of the ground motion service in Germany, which we call BBD. This is just the German word of Bodenbewegungsdienst, and because this is a national project, and the spreading process of the idea and the lessons learned. And here on the left-hand side, you see, no, this is the wrong button. You see those permanent scatterers. These were generated from satellite data, and you see here in red subsidence of the ground, and in blue is the uplifting of the ground, and in green means almost no movement. This is just to get you accustomed with the colors that are used throughout the talk. Okay, what kind of ground motion processes do we have? We have almost no earthquakes, so we don't have fast ground motions, but slow ground motions, and those ground motions have mostly geological reasons. For example, again, the wrong button, the mining or abandoned mining, for example, here in the Ruhr area, but also gas extraction, salt extraction, and other mining activities. Peat areas or soil compaction, mostly at the coastal zones and then the German lowlands, and landslide hazard in the mountainous south, and salt and carbon structures which subrode and thus produce subsidence on the surface. So quite a large area and a geologic problem. And how is the manifestation on the surface? We have, for example, the mining or the filling or caverns in salt domes, and the caverns contract, and the contraction makes a subsidence bowl on the surface here. And from the subsidence bowl, you get maybe some damage in buildings and so on. And so we got to have some neutral assessment who is responsible, for example, for the subsidence and who is responsible for the damage. And there are also peat areas and soil compaction, and this is the difference. This is natural subsidence and this is non-natural subsidence. So for this somebody has to pay for, and for this maybe not. And this is landslide hazard, for example, the moving of vineyard walls. And even this tower is more oblique than the Tower of Pisa, which is due to salt and carbon structures subrosion. And so the church tower is going to get oblique. So assessment of ground motions a few years ago, how was it done? The state and municipal authorities are responsible for the neutral assessment of causes. So they find out who has to pay for the damage. But what we see, those are not neither national authorities nor academia and universities. This is important, not academia and universities and not national authorities, but let me say state authorities, and we have 16 states. That means 16 geological surveys, 16 geodetic surveys, and 12 mining authorities. It means about 44 authorities that are responsible for ground motion assessment in the country. So there are capacities and numerous classical methods to cope with ground motion and geohazard that exist. And the applicability of radar interferometry, or this is the other word, of INSAR. There will be a talk at 17 hours this afternoon where Thomas Fuhrmann from the GA Australia will dig in a little bit more into INSAR, and you can see me also at the at the EU booth to talk a little bit more about the technique. This is somehow known, but neither experience or nor trust in workflows and norms exists at those authorities. So, but there are numerous academic and test pilot cases where the application is shown and the applicability is shown. So those are EU projects for national authorities, academias, SMEs, so for those and not for the ones who are responsible for the things. So the INSAR technique is almost not applied in the day-to-day business of state and municipal authorities. And this was the reason why we were doing the national ground motion surveys. So those affected population, economic and infrastructure, who pays for the damage. This is high public attention and political relevance, so a high demand for neutral frame. So this is a public task. So this is something for the federal institution. And the INSAR application is mature, measurement accuracy is proven since 1995. And the data with the Copernicus program from the EU are now freely available and recorded every 6 years, and they are available guaranteed until 2035, which is a real game changer. And so we provide a frame and to foster further developments, create added value for public and private sectors, and the pilot studies, which is important, generate interpretation skills in those 44 authorities and method experience, which is also very important. So how to do this? Get an official mandate. There was a national program of Copernicus measures in Berlin, where we got the mandate. 2012 it was, I suppose. So this is the thing that Pascal told this morning, and this is the time it takes. 2012, we have now 2019, 7 years of work. So gather expectation, listen a lot to the national, to the federal state authorities. What is the problem? What can we do to reach usability of the EU data? So listen a lot. And collect the requirements. So we made several Copernicus workshops with the users and to gather their requirements to find out what do you think, what do they think what usability of data is. And do feasibility studies and elaborate the concept of the German ground motion service that bases mostly on the, wrong button, again, on the Copernicus data, which is the nationwide medium resolution PSI product, which is another word for radar interferometry. And there is another part, the orange one, which shall be operated by private industry. So we won't take away business from private industry, but foster business for private industry to, because we generate a neutral framework, and private industry can then generate Zoom products in space and time to have their business with it. So, and then let the concept be blessed, get a lot of discussions about the concept, make those walls and have those discussions here, discuss with the media, for example, is the concept right, go to the field with the state geological surveys, find out what can they see, what can they not see, and make the concept even better from those words on, and allocate resources, which is also very important, get the money from the ministry to do the concept. So build the knowledge and know-how, so invite the state ministries and the director circle and do those working groups and discuss a lot of things, do the, let me say, the brokerage, how to use the data, what is data usability, have the seminars with all these things and seeding the knowledge and the administration, do easy-to-use applications, ready-to-work applications with added value for specific regulatory or maintenance tasks. What are the regulatory and maintenance tasks? So this is important to know. Inspire the permanent staff, which is also important. Their supervisors and the directors for the usability of the EU data, and not only to the project staff, because the project staff is gone after 3 or 4 years after the project ended. So you have to concentrate on the permanent staff and let them recognize the advantages for their daily work. And one problem that we faced is the state and municipal travel expenses. So sometimes it's too costly for them to travel from southern Germany to northern Germany. So those are sometimes problems you don't expect. So just, and that don't have to do with technical reasons. So, and spread the knowledge and enable discussions. So workshop with authorities, industry, and academia. So we did a lot of pilot studies and listen to the practical needs and present at non-remote sensing symposia and conferences, for example, at coastal engineering and geotechnics, at rock mechanics, geophysics, and mining, and collect the questions the people and the users might have. And to spread it to the continent, let EU Commission in Brussels note about the things we do. So right now there is a tendering process underway for the European ground motion service by the EU mission. And then we have 40 pilot studies spread all over Germany, all over the geology of Germany, and we needed to get geologic quality assurance, the data usage and the day-to-day applications, establish personal networks, which was also very important, and build experience, interpretation skill and experience in those state surveys and some federal institutions all over the country. And there's just one example that you see for the applicability. For example, there's a new McDonald's here that was built on compactable ground. The building was founded on pillars to the stable ground, but the parking lot was not on the pillars. And what you see here, you have these green, not moving dots and red dots were syncing close to each other, and everybody would ask, how is it possible? Moving something and not moving something close to each other. So you have to go out, see there's something going on, and what's going on. So the parking lot is moving downside, and if you have a drive-in, at some times you would reach up to get your burgers from the McDonald's afterwards. So this is quite usable for the local authorities, and this is what we call bridging the gap between the scientists and the practitioners, because those, again, the wrong one, because those practitioners look at real problems. They have something to solve in the real world, and don't have to do only their master thesis. And they found out radar interferometry, or INSAR, or PSI, is an additional method, not the only method that is applicable, method for detection and monitoring of ground motion. It has a high repeat circle, other than leveling, for example. On otherwise maybe inaccessible ground, you can look backwards in time because the data are generated anyway and has values for large areas and is reliable, free, and open data, and you can concentrate your more expensive methods at most interesting points, for example, leveling campaigns. And, as I said, to bridge the things between practitioners and space geeks that have a lot of fun about their new mainframe, and the practitioners won't understand this fun. So the transfer of data and knowledge into the heterogeneous administrative environment, so this is called public consultation, is not science and research like scientists and researchers understand it. It's another kind of work. It's also hard work, but you have to do other things. So there are disappointments due to high expectations by the practitioners. There's a geodetic accuracy is expected. You got wrong interpretation of colored PSI is often very awkward. Not every ground motion can be monitored. Not every scatterer can be found in the field. And remote sensing specialists are rare in this environment. And this is maybe also for Europe, speak the native language of the potential user. Not every potential user in Europe speaks English. There are Germans, French, Italians, and Czechs, and this is also a barrier sometimes. And so the summary and the take-home message is the consistent PSI dataset for the whole German territory, which is the size of Victoria, I learned yesterday, so quite small. So, and is available. Interpretation skills for everyday work are hard to build in the state administrations. And what I also say on what the first speaker mentioned, this EO technique or radar interferometry must be easier to use. So we need some kind of, let me say, smartphone moment because we all need navigational system. This is also very complicated, but it is now so easy that everybody can use it. So we need, for example, between the customer and the user, some kind of small and medium enterprise, or let me say broker, and the SAR specialist, some kind of bridging that makes it easier for the geologists to use the SAR or interferometric data for their everyday use. So thank you for your attention, and if you have questions, see me at the EU booth or look at those link. Thank you very much.
Thank you everyone for presenting and coming along this morning. Morning tea should be on now if you want to jump outside. Thank you.